hopefully we'll be finishing the rotational dynamics today. I think we did an example before, so, and I'm going to just very quickly say about the conservation of angular momentum. I hope by now you're convinced already that angular momentum is a conserved quantity, like the conservation of momentum. Okay, and this is one of the three fundamental laws of physics, fundamental conservation laws: the conservation of energy, the conservation of linear momentum, and the conservation of angular momentum. And it has been tested on a variety of scales, from atoms and nuclei to galaxies, and no exceptions in terms of the conservation of angular momentum has been found to the moment we speak. Okay, so momentum is conserved. What does it mean? Very similar to what we mean by the conservation of linear momentum. If there is no net external force, if the net external forces are zero of a system of particles, and then really then conservation depends how we define the system. Okay, so if we draw a boundary around a system of particles and there is no net force from outside across that boundary occurring or acting on the system, then the linear angular momentum of that system would be conserved, and its sum would remain constant as a function of time, as the system evolves in time. That doesn't mean that all the internal forces have gone to zero as well. So system parts of the different particles or bits of the system can be exerted forces on each other, but the net momentum would remain conserved. And this is exactly what happens with the angular momentum, with the only difference that once you have the angular momentum, it is not the net external force, but it is the net external torque that has to be zero. If the net external torque on a system of objects or particles, whatever you like, once you draw a boundary, okay, and then there is no torque coming in or going out of that system, then within that system, the linear angular momentum is conserved or constant in time. And if you want to see it more formally, this is what it means. So if the sum of all external torques, that is what the fundamental law of rotational dynamics is, that sum of all external torques is equal to the time rate of change of the angular momentum. All right. And then if all the net external sum of all the external torques is zero, then this means dl over dt is zero, and that necessarily means L is constant. Okay, or in other words, it's conserved. Okay, is this clear to all of you, or do you need me to do an example as well? We have done one example in one of the recitations as well. Okay. Okay, I'll just draw it for you, and then you can do it yourself. So let's say that you have a vertical spindle, okay, and you have a disc around this spindle, okay, that is rotating, let's say, with omega 2, and its moment of inertia is I2, right? And then we have another disc on that spindle, okay, which is rotating with omega 1, and with its moment of inertia is I1, right? Now let's say that this is rotating, okay? So it has a certain angular momentum. What is its angular momentum? I2 omega 2, no? That's its angular momentum. Okay, and let's say that this disk is rotating with a different angular speed. At some point, we release this disk and we let it fall on this other disk, okay? And let's assume that the force, the friction between the two disks, the surfaces of the two disks is large enough that the moment that this disk falls on this disk, they start rotating with the same frequency, with the same angular frequency without one sliding against the other, all right? If that happens, then the initial angular momentum, Li, is nothing but I1 omega 1 plus I2 omega 2. And the final angular momentum in this case, what would be the final angular momentum? Two disks touching each other on top of and rotating with the same frequency. Quickly, come on.
I said
I1
I1
plus
plus I2
I2
omega.
Again, one by one. So first, Amina.
I1 plus I2 omega.
Yes, good. I1 plus I2 times a common frequency, omega. All right. And then you can come up with various relationships. And we know that Li would be equal to Lf. And now you can use this relationship. If, for example, you are given the initial frequencies and you want to find the final frequency, including the case if the upper disk was not rotating at all and just falls and the lower disk was rotating, you can analyze all those cases by using these two equations, okay? This is what conservation of angular momentum is, and this is how you are going to use it. It's very useful when it is very hard to find out torque, for example, okay, or to know torque. And then when you can just use the conservation of angular momentum to solve this problem. Any questions so far?
Sir, how did you equate Li is equals to Lf? वो किस से किया है?
Because of the conservation of angular momentum, that the angular
Alright.
momentum before and after should be equal, and that is why. So we are taking advantage of that fundamental law. Okay.
All right.
Okay. So now I want to start something very interesting and important. But before I do that, let me just say something. So you already know this relationship, which is nothing but Newton's second law. Okay. Time rate of change of linear momentum, okay, is equal to the force being applied to the object. Okay. What that means is that if an object is moving, let's take a particle with a certain velocity v, okay, and then it has, of course, momentum mv, which we call p, all right? Now, there are two ways to change momentum. What are those two ways?
Change in mass and
velocity or
change in
change mass.
velocity.
Yes, we can change its magnitude, okay? So we'll have to exert some force in the same line as the velocity. So if we apply the force in the direction of the velocity, its velocity would go up and momentum would increase. We can apply a force opposite to that direction, okay? And we can change we can decrease its velocity, okay? And that would effectively only change the magnitude of the velocity. It does not change the direction. But then we can apply a force at an angle, any angle, compared to the relative to the direction of motion. And if we apply a force at an angle, whatever angle we apply the force, it would also change the direction of the particle or change the direction of the momentum. Okay, so change in momentum here means both. If we want to change the direction of the momentum, whether we want to change the direction of the momentum or magnitude or both, we need an external force. Why I wrote this is because the same is true for angular momentum. So if you have this fundamental law of rotational dynamics, that if you want to change the direction of the angular momentum or its magnitude, you need a torque. Okay, without a torque, you cannot. So in a way that the Newton's law says that you need a force to change the state of motion of an object. If you have no force, an object would continue moving with the same momentum. In a similar way, if you need to change the angular momentum, whether direction, magnitude, or both, you need an external torque to do that. Otherwise, it continues, the object continues its state of rotation as it would continue its state of linear motion without a force. ठीक है? After having said that, now we learned something, a phenomena and an instrument. The phenomena that we are trying to, yes?
अगर हम एक एक्सटर्नल टॉर्क ऐड कर देंगे तो इससे आपका जो एंगुलर मोमेंटम है वो इंक्रीज हो जाएगा, है ना? तो
जी, क्या
अगर
दोबारा क्या?
मैं कह रही हूँ अगर आप एक्सटर्नल टॉर्क ऐड करेंगे तो आपका जो मैग्नीट्यूड है एंगुलर मोमेंटम का वो इंक्रीज होगा, है ना?
Not necessarily, it can just change the direction.
चलो, मतलब उसकी बेसिकली वैल्यू चेंज होगी एंगुलर मोमेंटम की, तो इससे फिर आपका वो जो लॉ है कि आपका एंगुलर मोमेंटम कंजर्व रहता है वो होल्ड करेगा कि नहीं करेगा? Because since we changed it with an external torque.
नहीं, but वो तो होल्ड कर रहा है ना कि if there is an external torque, then it would change by the same amount. Okay, what is this?
मतलब आपका जो एंगुलर मोमेंटम कंजर्वेशन है वो तो यही है ना कि आपका जो इनिशियल एंगुलर मोमेंटम है वो फाइनल के इक्वल होगा
When there is
तो
no external torque. When there is no external torque.
हाँ, तो मैं यही पूछी थी कि आप एक्सटर्नल टॉर्क डालेंगे तो ये लॉ होल्ड करेगा कि नहीं करेगा? तो फिर नहीं करेगा।
Of course करेगा,
of
course नहीं, देखिए of course करेगा, मैंने कहा है कि यूनिवर्सल लॉ है, आज तक किसी को एक्सेप्शन नहीं मिली. The difference is that then we would know exactly how much the torque has added to the angular momentum.
सही, ठीक है.
So look at this equation. Okay, so let's say that your initial angular momentum is Li. Okay, and now in the meanwhile you have applied some torque. Okay, and that torque is tau. That's exactly this. Then you have to, yes, you bring dt here, and that is the amount by which you have changed the angular momentum, added to the initial momentum, and that would be equal to the final momentum. So it still holds. You see, this is law of conservation of angular momentum, and you have an external torque present.
सही, okay.
Okay. But now we can account for the change, where it is coming from. It's coming from torque. So set the external torque to 0, you get Li is equal to Lf. You have torque, then you have to integrate. Let's say in this case, I'm assuming the torque is constant in time, but otherwise you should integrate, okay, this, and whatever angular momentum this torque has given to the system or taken from it, okay, you account for this, and then you still have this equation. So conservation of angular momentum still holds.
Okay.
Okay, so an instrument called gyroscope. Have you heard of it? Seen it? Okay, gyroscope. And the phenomena that we are trying to understand, well, we'll introduce once we get to it. All right. Gyroscope. Okay. Now let's say that we have this situation. We have a sport, and on the sport, we have a horizontal rod pivoted. All right. Let's say that its distance to its center of mass is L. Okay. And at its center of mass, we have a very heavy wheel, a flywheel. attached. All right. And here we have a sports stick. Okay. Now, let's say that this is our ground. Right. And the moment I remove the sport, this is all here, nothing moving. The wheel can rotate, but it's not rotating. Okay. What happens the moment I remove the sport? We've done this before, right?
Obviously आपका wheel जो है वो नीचे गिर जाएगा.
The wheel would just simply fall down because there is a force acting mg downwards. Okay. And it's so this tip of the wheel would be making a radius like this, right? Can you help me calculate the torque due to gravity? Please.
Sir, zero होगा.
Zero hoga. Who is this? Naam apna, can you introduce yourself?
Sir, Fahad. Fahad.
Fahad, नहीं zero नहीं होगा. क्यों zero होगा Fahad?
Sir, वो center of mass में से नहीं pass कर रहा.
Center of mass से क्या pass कर रहा है?
Wheel.
हाँ, लेकिन मैं तो इस पूरे सिस्टम का कह रहा हूँ ना. अब ये इसकी फोर्स ऑफ ग्रेविटी है. ये पिवट यहाँ पे है. वो स्पोर्ट रिमूव की है. ऐसे गिरेगा तो क्या होगा?
Sir, wheel center of mass attach है कि यहाँ पर free move कर सकता है left right.
नहीं वो फिक्स है. फिक्स है.
ठीक.
क्या टार्क होगा?
Sir, फिर MGL हो जाएगा.
MGL. बिल्कुल इस तरह के systems के लिए we have done this before. Whenever you have a system like this and your force of gravity acting, you can assume that all the forces acting as if all the weight, total weight of the system is acting at the center of mass of the system. And yes, and basically then you multiply it with the distance to that point to calculate the total torque as if the torque is acting at the center of the mass. तो उसका magnitude क्या हो जाएगा? MGL. Very good, eh? Very good. So force is in this direction and L is pointing in this direction. What is the direction of this torque?
Clockwise.
Clockwise? Really? No. Think about it. The force is in this direction and L, the distance from the axis of rotation is L in that direction. The force की तो torque की क्या direction होगी? This is not very reassuring for me as an instructor in the second or third last lecture. Huh? Come on.
Sir, into the plane.
Into the plane. Yes, very good. Why? Would you like to explain?
Sir, because the right hand rule, we curve our fingers in the direction of the motion, the force. It's moving clockwise.
Yes, just like this. You put, my thumb is now pointing into the plane. ठीक है? Is it clear to everyone? It's not. You see the definition of the torque is R cross F, right? And the cross product of two vectors is always orthogonal to the plane of these two vectors. Now both L and F are in this plane. Okay. The torque has to be either outside or inside into the plane of the board. Okay. And as you can see, the right hand thumb rule is that you put the vectors, two vectors, either emerging from the same point or converging to the same point. So if I draw MG and L as emerging from the same point and then apply the right hand thumb rule, okay? So from L to F, okay? Going from L to F, okay? Curve my fingers, the thumb points inwards, okay? Into the plane. If this is, let's say, y-axis, and if this is, sorry, if this is x-axis, as we usually do, this is y-axis, then the z-axis is perpendicular to the plane of the board, all right? And if z is perpendicular to the plane of the board, then positive z is coming out and negative z is going in. So what is the unit vector here? Ez, and into the plane, negative indicates that it's along negative Ez. If this is not clear, please stop me here and let's discuss this, because this should not be much difficult to decipher. Okay, now we know that change in angular momentum is equal to the torque acting on this system, okay? So first of all, what is the angular momentum before we remove the support? What is the angular momentum of this system?
Zero होगा.
Zero hoga, right? So, but let me just calculate the change in angular momentum, and I'm just going to write dl is equal to tau dt, okay? That is the change in angular momentum. And now I know what tau is. So the change in angular momentum is mgl dt, okay, and ez. Okay? This is dl. This is the change in angular momentum, delta L. And if since initial momentum is zero, that's actually the momentum, okay? After I remove the support, okay? So after I remove the support, this would be the momentum. ठीक है? If this is not clear, now is the moment, okay? And
Excuse me, sir. इसके अंदर हमारे पास जो टाउ की वैल्यू है वो कांस्टेंट नहीं रहेगी, क्योंकि द वेट एंड द लेंथ बोथ स्टे कांस्टेंट है ना?
yes, tau की वैल्यू कांस्टेंट है, नजर भी आ रही है कांस्टेंट है.
एल ओवर टी जीरो नहीं हो जाएगा, क्योंकि मतलब बल्कि नहीं एल जीरो हो जाएगा ना इस तरह तो.
नहीं, क्यों जीरो होगा? कुछ भी नहीं जीरो होगा. देखें, वो तो L तो कांस्टेंट नहीं है ना, टाउ कांस्टेंट है और टाइम डेरिवेटिव तो L का है, और मैं तो उसके अपोजिट कर रहा हूँ. आई एम ट्राइंग टू इंटीग्रेट.
बिल्कुल. थैंक यू सर.
So dlz is equal to minus mgl dt. Again, वो पिछली जो इक्वेशन अभी की थी कि dt times the torque gives you the change in angular momentum. Okay, moving on. Now let's make the situation a little bit complicated, okay? Now what we are going to do is, we have, let's say, a motor, that external motor that we can use, and we spin this wheel, okay? We spin this wheel at a frequency omega around this rod, okay? Very, very fast. And let's say that its moment of inertia is I, the moment of inertia of the wheel. And we spin it with the angular frequency or angular velocity omega very fast. And let's also assume, okay, that the mass of this wheel is much, much larger than the mass of the rod. Okay? And now we spin it. Okay? And after spinning it very fast, I remove this support. What happens then? Would it fall down?
नहीं sir, it would keep spinning, I think, on the rod.
Why? just spinning or something else as well?
सर आई थिंक वो फौरन नीचे नहीं गिरेगा जैसे पहले गिरा था.
ठीक है, it would keep spinning. Okay, that's a good answer. Any other answers?
तो जो स्पिनिंग वाला मोमेंटम होगा वो मेरे ख्याल से इस वाले मोमेंटम को कैंसिल कर देगा और फिर वो रॉड ऊपर वर्टिकली रहेगी.
ऊपर चला जाएगा,
नहीं मतलब है इसी हाइट पे रहेगी.
इसी हाइट पे रहेगी, इसको कैंसिल कर देगा. That's also a reasonable answer, although not correct. Both answers are not correct, but it's a good answers actually. Very not completely uninformed. Any other answers? Any other guesses? Okay, let's see this. Achha, let's we have now angular momentum associated with the wheel. Okay, what is its direction? The direction of the angular momentum. Sorry, before I go to that, remember this: the angular momentum of the falling of the whole assembly in this way under the action of gravity, the direction of the angular momentum you see is still into the plane of the board. Not just torque is into the plane of the board, but angular momentum is into the plane of the board, okay, due to this falling. Okay, and now keeping that in mind, Fahad, can you mute?
मेरे ख्याल से
Fahad, can you mute your mic, please? All right. So now we need to figure out the angular momentum. Well, we know the angular momentum of the rod is just L omega I, right? Or I omega. But what is its direction?
सर मोटर किस डायरेक्शन में स्पिन कर रही है?
Very good. Yes, that was the missing information. Okay, let's say that we are rotating it anti-clockwise. Okay, if you look at from this side, from the front, okay, it's rotating this way, anti-clockwise. सामने से देखें तो ठीक है. तो अब क्या डायरेक्शन होगी इसके एंगुलर मोमेंटम की? If I want to write a vector here, what would be the unit vector here?
EX में आ जाएगी.
EX. Very good. ठीक है. Now we have two angular momenta, DLZ, okay, and the angular momentum due to the spinning of the wheel. Okay, let's play with them. So now the moment we remove this support, what is the angular momentum? Because we have already put this into spin. This is our Li. Okay, this momentum is already in the system. Okay, and then this momentum is what the system would acquire after the support is removed and it's falling down. Okay, this is the momentum the system would acquire. That momentum is already there. So the sum of these two momenta would be the final momentum. In other words, we get this equation LF is equal to Li plus delta L. And if I want to write explicitly, this is I omega EX minus MGL delta T, okay, times EZ. ठीक है? And this is LF, the momentum after removing the support. If this is not clear, now is the time.
ये नेगेटिव क्यों इसमें हो गया? माइनस क्यों कर रहे हैं?
माइनस देखें, जो ओरिजिनल वेक्टर लिखी थी हमने वो चूंकि इनटू द प्लेन है, इस वजह से नेगेटिव है. यहां से लिखा है because it's into the plane.
ठीक सर।
ठीक है? So if you were looking at this assembly, sorry, if you're looking at this assembly from the top, okay, this is how it would look like. This is the pivot, okay? If you're looking at from the top, this would be I omega, okay? Now we said that the wheel is much heavier than the rod, and we have spun it at a very, very high frequency, okay? So then this would be I omega, and remember, we are looking at it from the top, okay? There would be a relatively small component into the negative z-axis. Now this is negative EZ, this direction, and this is EX. And we are looking at the assembly from the top. The wheel is somewhere here. Okay. And the two components, this one is pointing along x-axis, and the component caused by the gravitational force that is acting downwards, okay? In this case, now gravitational force is acting into the plane, okay? Because I'm looking at from the top. This is top view. And then there is this delta L is here. This is delta L, and this is I omega is Li. Okay, initial momentum or the momentum due to the spinning of the wheel. And we have deliberately chosen this component to be large. Okay, we have spun it very fast. All right. So the resultant angular momentum has moved here. The result, okay? Because this component is small, this component is large. The total angular momentum LF would be here, no? The sum of these two, the vector sum of these two. Okay. Now, if I go back, here, the force of gravity is pulling this assembly down. And when this wheel was not spinning, that's what happened. It fell down. But now it has a huge angular momentum in this direction. Okay, a huge angular momentum in this direction. When the gravity acts, when the force acts, it doesn't simply pull it down. Okay, it exerts a torque that is into the plane. Okay, but angular momentum, this is a huge angular momentum whose direction the gravity is trying to change to pull it downwards. All right, to pull it downwards. But this has an angular momentum, and then the pull downwards of the gravity creates an angular momentum into the plane. Okay, that results the angular momentum turning away, going into the plane, not going down, not this object going down. Or in other words, the angular momentum resists change in its motion. Okay, it resists change in its motion, and it tries to counteract the torque that is acting inwards. Okay, and what happens is that the rod ends up moving inwards. The rod ends up moving into the plane by a small amount. Okay, once it has moved, you can think of this as a sequence of events. The gravity acts, adds another torque, so it's like this. Now the rod is at some point, after some time, the rod itself comes at this position. Then we have a torque acting in this direction. Then it rotates. Then we have a torque acting in this direction. It rotates. the rod rotates, okay, while it is spinning, okay. And then if we try to drop this assembly, remove the support while the wheel is spinning very fast, instead of falling down, it doesn't fall, one, somebody answered this already, but it also starts precessing. Precessing means the rod starts going around like this. It wasn't in the camera. So if the rod is on my arm here, sorry, the wheel, okay, you remove the support on the other side, without any motion, it just falls down. With the spin of the wheel, what happens is it starts going like this. Doesn't fall down, but it also goes around the rod, okay, and that is what is called precession.
It keeps precessing in the same direction. मतलब अगर clockwise inward move किया तो वो inward ही रहेगा.
Yes. So that precession's direction you can change by changing the spin of the wheel. If you spin the wheel in the other way around, then it would precess in this direction. So that really direction depends. We'll get to the frequency, and you see the direction of the precession depends on the direction of this velocity, angular velocity of the wheel. So you can change it, and then you will have the precession in another direction.
एक्सक्यूज मी सर, आप ये एक दफा दोबारा प्लीज बता सकते हैं कि आपका जब एक बेसिकली फ्रिक्शन की वजह से जो टॉर्क है वो टुवर्ड्स द नेगेटिव जेड एक्सिस है, और जो इसकी रोटेशन की वजह से टॉर्क है वो टुवर्ड्स एक्स एक्सिस है, तो उसके थ्रू मतलब वो आपने कहा है ना कि वो इनवर्ड मूव करता है टू रेजिस्ट द मोशन, तो आप प्लीज दोबारा बता सकते हैं?
देखिए इसको, I know that this is a little bit abstract. Okay, so do you see this, that this is the torque along x-axis? We are seeing it from the top, okay, the assembly,
Yes.
okay, seeing from the top. This is the angular momentum. Angular momentum is along this direction, okay,
बिल्कुल.
and the angular momentum of both the torque due to gravity and the angular momentum due to gravity, that small angular momentum, this quantity is along negative z axis. And now the resultant would be here.
सही.
All right. So what is happening is that the rod adjusts itself, okay, to respond to this torque, and it can only do that if it moves where the resultant vector is.
सही. तो
Okay.
बेसिकली जो आपका नेगेटिव जेड एक्सिस में टॉर्क प्रोड्यूस हो रहा है वो उसको रेजिस्ट करने के लिए इट्स मूविंग टुवर्ड्स,
या उसको
मतलब
रिस्पॉन्ड करने के लिए you could also use वो स्टार्क का एक्शन इसके ऊपर है कि was moving it in that direction.
ओके.
ठीक है. So and this is called precession, okay, and this is the basis of a very useful device called gyroscope, and I'm going to send you a link right away, and I encourage you to watch this video on your own on your laptops right away, because that's a very nice demonstration of what we just did. Okay. I'll give you a couple of minutes to just quickly watch it. Okay, I'm sending the link in chat.
सर ये मैंने कंफर्म करना, तो प्रीसेशन तभी होती है जब जो EX वाली एंगुलर मोमेंटम होगा वो बहुत ज्यादा हो जाएगा इजी वाले से.
We will talk about quantitatives in a minute. So first have a look at the video. Quickly, please. Did you get the link, all of you?
जी सर.
Please play it on your devices, okay? You can fast forward it to like 40 seconds, for example, or 45 seconds. All right, so we'll continue onwards. The second is just changing the direction of the precession, the second attempt. So we'll just move on. So did you see that one end is sported and the other end is not sported? And if you just put the wheel inside, we'll see it just falls down. But if you rotate it first before placing it in the assembly with one end sported, another end open, you see that it keeps gyrating or it keeps precessing and it doesn't fall down. Okay. Any questions? All right. So if this length, if this length is Li, okay, and this length is approximately dl, the one we have here. Okay, so what is the angle then? The d phi that the angular momentum vector makes its with its previous position.
So tan inverse dl over li.
Yeah, but we can use something more simpler. Let's say that the arc here and the straight line are approximately the same because the angle is very small. So what would be the angle then? The arc dl, the magnitude of course, would be equal to Li magnitude d phi, no? यही arc का formula है ना?
yes sir, यही बनता है.
यही है ना? So from here you can write d phi dl over Li, all magnitudes, huh? And what is dl? dl is mgl dt, no? mgl dt, right? And what is Li? I omega. यही है ना? Okay, let's divide the whole equation by dt. Okay, and then this side dt cancels, right? We get mgl over I omega. And what is this, anyone? The time rate of change of this angle that the rod is making with its initial position.
ओमेगा हो जाएगा.
What omega? This is precession frequency denoted by capital omega. Okay, this is the frequency of precession. Okay, the frequency with which the rod goes around. Okay, and now you see the quantities it depends on. Okay, it's inversely proportional to the rotational frequency or the angular frequency of the wheel. Okay, the faster the wheel moves, the slower the precession is. Okay, and the slower the wheel is, the faster the precession is. Okay, this sounds counterintuitive, but if you ever played with the top, if you spin the top very fast, initially it's very stable. There is no wobbling, and the reason because there is no wobbling is because the precession frequency is very small. It doesn't precess much. It almost stays there. But as the spinning top, due to friction, that becomes slower and slower, you see it becomes wobbly. It becomes it starts precessing very fast until actually the frequency is zero and it falls down. Okay, this is the reason. This relationship and this precession is the reason for the stability of the vertical stability of spinning objects. When you spin a top, why does it keep spinning and doesn't fall down? Because it has a strong angular momentum in this direction. Okay, and this is also the basis of a very important device called gyroscope, because in gyroscopes what they do is they have something very heavy and very Then they spin it very fast, and then they attach 3 axes to it. So that, and then the gyroscope is then mounted on, let's say, on a spaceship. And once a spaceship goes out, the direction of the spinning object would continue to remain same, doesn't matter which orientation the spaceship is moving, it would preserve the orientation. And you can figure out your orientation relative to where you started. Okay, if you started on Earth and you chose a particular orientation, doesn't matter wherever you in space you are, you would still be able to find out your orientation with respect to Earth. Okay, and I invite you to watch the nice videos about gyroscopes and how it works. Okay. One more thing here about this assembly. Since this is not falling down, the normal force provided by this support is equal to the weight of this whole thing. All right. This is important. And another important thing is that when this is spinning around, okay, this thing is spinning around, it has a centripetal acceleration. Okay? And to provide centripetal acceleration, this support also provide a contact force. It has to hold the assembly, otherwise it just would fall off. So the centripetal force provided by the pivot, in addition to the normal force, that is equal to mg. This is very important for problems that you may see in your exam or in your quizzes, that the force provided by the support is equal to the weight of the whole assembly, and the contact force in this direction provided by the support is equal to m omega square L. Okay.
So ये basically उसकी centripetal force होगी of the system.
Yes. Yes. The contact force.
Sir, can you explain the m omega square L? That's the centripetal force or the contact force?
Well, it's the same thing. I mean, it's a contact force. If it is, look, if you attach a stone or a ball with a rope and start rotating it like this, swinging it like this, you see, if you cut the rope, the ball would fly away tangentially, right? So the rope is providing the inward force, otherwise it won't stay in the circle. Okay? And that force, that's what I'm saying here. So it has to hold on to it. And this is also another example. When you have a stone and you rotate it around constantly, okay, with a very high speed, the stone doesn't fall down. Okay, but the moment you stop rotating it, it would fall down. This is another example of precession. This is not precession, but since you have angular momentum, so the gravity does not get to bring the stone down.
Okay, thank you.
Okay, so the next thing is
So I have a question.
yes.
Okay, so like a really dumb one, but in the first case, when we weren't like rotating it, we just removed the spot. So in that case, angular momentum was into the plane, right? Easy. Then why did it just fall down? Why didn't it move into the plane, the wheel?
But angular momentum is always orthogonal to the direction of the motion.
Yeah.
So that angular momentum is not making the wheel go into that direction. Okay.
Mm. Okay.
So so a little bit about the orbits of the the planets, okay, around sun or moon around Earth. All right. So when Newton was applying his theory to the orbits, his theory of so he realized, Newton, that if this is Earth and this is moon, okay, the moon should travel in straight line, right? Because that is what his first law says, right? That an object would continue its state of motion. That includes both the direction and the magnitude, right? So the moon should stay in the straight line, but it stays it actually goes into the orbit. That is when Newton realized that there was a force acting on the moon, okay? An attractive force from Earth that was pulling the moon and keeping the moon into the orbit, okay? And then in a way, Newton realized that this was not very different from an apple falling on the Earth. This moon was falling under gravity, okay? And he wanted to calculate, okay, by calculating the distance apple would fall in 1 second, he wanted to calculate how much distance moon would fall in 1 second. Okay, is the problem state clear?
Sir, could you repeat
Yes.
that?
Hmm?
Sir, could you repeat it once again?
So again, I'm saying Newton realized that if you held an apple here, it would fall down on Earth, right? But then Newton questioned that moon was moving and it should move in a straight line. If it was not going in a straight line, but in an orbit around Earth, that means it was the same force, okay, that was pulling the apple towards the center. That was also the same force responsible for keeping the moon in the orbit. Okay, so what his conclusion was that both objects were falling towards Earth. One actually falls on the Earth and hits it, and other almost never does it. So we will see why it doesn't. Okay, but then his question was, can I calculate the ratio between this apple falls in 1 second with the ratio with how much moon falls in 1 second? Right? That's what he tried to do. So it's very simple. Now we know that an apple, let's say SA falls half GT squared, okay? That's the relationship between distance and, now we know that G is G near the surface of Earth, ME over R squared, RE squared. All right. This should be, I mean, the G is a very fixed value. I should actually write it like this. Yeah, this is G, that's fine. But the gravitational acceleration in general should be written like this. G ME over R. The distance of the object, wherever the object is, okay? In case of moon, this would be the distance from the center of Earth to the center of moon. And let's call it RM squared, okay? Now, the distance that the moon would cover, the equation is the same, okay? Half AT squared. But what about, can you tell me which is larger, A or G?
सर A larger होगा ना, क्योंकि नहीं G larger होगा क्योंकि R M.
Because the distance to the moon is larger than the distance the apple has from the center of Earth, right? That's RE, this RM is larger. So the A would be smaller. So that definitely means that moon would fall towards Earth a smaller distance in 1 second than an apple does, okay? Now let's try to calculate this. This you can actually calculate. What would the apple fall in 1 second? 4.9 meters, no? Or 16 feet. In 1 second. This is easy. Now, if we take the ratio of these two quantities, SM over SA, that would be simply equal to RE squared over RM squared. All right. Now, Newton luckily can calculate SA himself. That was very easy. He knew it. You could calculate from his equation. RE and RM were known to him from Greeks and Arabs had calculated these two quantities and verified using the lunar eclipses. So he had access to both of these quantities. He knew what they were, and they were the RM, the distance of the center of mass to the moon, was simply 60 times the radius of Earth. Okay. And if you plug that in and this number, you would get the distance that moon would fall in 1 second. Okay. Can you calculate that quickly?
So ये हो जाएगा 16 over 3600 feet, I think.
Yes, but you it's just one because this is cancelled, right? The RE cancels, and you have only 1 over 3600, right? Times SA. So आपको सिर्फ इसको 4.9 को 3600 से divide करना है या 16 को, ठीक है? Because I have the answer in inches. I used an old book, but you are welcome to use the SI units. Okay, the moon falls 0.05 inch in 1 second. Okay, this was Newton's prediction. All right, and now let's see. We calculate the same thing using a different approach. Okay. Now let's say this is the orbit, and Earth is here, and this distance is RM. Okay. Someone is not muted, please. Okay. And then this distance. Let's say that in 1 second, this much angle or distance the moon moves. Okay. It moves from here to here. Okay. So if we were speaking strictly, this is the distance D. That would give you the fall, strictly speaking. Right? And this is, sorry, this is the fall. This is the distance it would cover if it went tangentially. Right? Now from here, I can write RM, and this of course would be a 90 degrees angle. Okay, that's the tangent. So I can write RM plus SM squared is equal to what? This total distance, this side squared equal to RM square plus D square, right? Isn't it? Just the
Sir, इसमें
Pythagoras.
ऐसा हमारे पास वो नहीं है arc length between the 2 points you do.
जी?
इसमें जो SM है वो हमारे पास मुझे एक दफा क्लियर कर दें, is SM the arc length between these 2 points?
SM is
या SM इस केस के अंदर क्या है?
ये डिस्टेंस है, ये वाला।
अच्छा, सही है।
ठीक है, and RM plus SM is just the side of a triangle. Okay, so RM plus SM square is equal to RM square plus D square. Now, if you open this square and cancel RM on both sides, you get 2RM SM plus SM square is equal to D square. All right. Now you see that this distance SM is very, very small compared to the radius RM or compared to D. So we just basically ignore it and we get the relationship for D as D equals D square equals 2RM and SM. All right. Now we know this ratio, okay? The distance moon falls in 1 second to the distance that the moon would cover in 1 month, okay? In 1 lunar month, that would be 2 pi RM, right? This is the distance it would cover in 1 second. This is the distance it would cover in 1 lunar month. And this ratio would be the same as 1 second over 1 lunar month. All right. Now from here, you can calculate that D turns out to be 0.63 miles. Okay. Once you know D, okay, now this is empirical. Okay, this is not a prediction of, we did not use any of Newton's laws here, okay, or any of Newton's equations. This is empirical, okay, from observations. If you use D, okay, and RM to calculate SM, this is as if you have measured this distance, and surprisingly or not so surprisingly, the SM turns out to be exactly what Newton's theory predicted. The moon would fall in 1 second by 0.05 inches. And this was a huge moment, okay? Getting a theory which was developed on Earth, mostly thinking about the objects on Earth, was able to predict very accurately the motion of planets, heavenly bodies, back in the years.
So, sir, you found D using the ratio and then you input that into the equation to find SM.
Yes.
Okay, thank you. Sir, how did you find the ratio?
Just using this equation that if the distance covered in 1 second and the distance covered in 1 month would be the same as the time ratios.
सर लेकिन when RM is unknown तो फिर आपने मतलब D किस तरह फाइंड किया? मैं भी फाइंड करने की कोशिश करें तो ये इशू आ रहा है.
देखिए RM तो we know, RM तो we know, okay. The only thing was D that was not known in this approach, okay. And then we calculated D and then we found back SM from here.
Where's the ratio assuming constant velocities?
Yes.
Okay, thank you.
So one bit that I did not emphasize is this, that Newton realized that basically if you stand on a mountain, okay, he realized that all these planets going around stars or satellites going around planets were actually projectiles, okay. And That was his calculation, that if you throw a projectile, it falls on the earth. Okay? If you throw it faster, it falls down farther away. If you throw it even faster, now it falls down further away, but now there is no more earth because earth has curved away. Okay. If you throw fast enough, then this object would never actually be able to fall on earth. It would start going around it. Okay. And then depending on how fast you throw something, the initial speed of the throw, okay, it could make a circular orbit around the planet. It could make an elliptical orbit if you throw it faster. It can make a, if you throw it even faster, then it would become a parabola or hyperbola. Okay, that really depends on the initial conditions. So that is what Newton's reasoning was behind that. Actually, all these planets around sun or the moon around earth were constantly falling, but they were never able to reach earth because earth had curved away from under them. Okay? That's why they never reached the surface of earth. Okay. And I just want to spend next 5 minutes very quickly saying a few things about Kepler's laws. I unfortunately didn't cover them in much detail. So now you know that if you have a circular orbit, then the acceleration, the centripetal acceleration is simply minus v square over r unit vector. So the minus here indicates that the direction of the acceleration is towards the center, opposite to the vector r. Okay, towards the center. Okay, we also know that F is equal to, the gravitational force is equal to simply GME. Let's say we are considering moon, MM over r squared. Okay, and r unit vector, right? And then from here, you can calculate that v squared is nothing but GME, okay, over r, right? And this is the velocity. This is the acceleration with which something moving in a circle falls towards the earth, falls towards the center of the circular orbit. Okay. If you equate that with the gravitational force and calculate the velocity, this is the right velocity. If you throw an object away from earth parallel to its surface, okay, from a certain height, it would never return to earth. It would start going into the orbit. That is the velocity which gives stable circular orbits. All right, just equating the centripetal acceleration with the gravitational force. Okay, and you see it would be different for different planets. For sun, it would be different. Something going around moon, it would be different because it depends on the mass of that object and how far the orbit is. Okay, further away the orbit, you can go slower. Smaller the orbit, you will have to go fast. And these are the basis of for all the man-made satellites that we send out. That is how we calculate what should be the speed to maintain a certain orbit at a certain distance r. All right. And from here, you can also calculate the period of rotation. Okay. Because you know A is equal to omega squared r, and that is nothing but 4 pi squared over t squared, okay, into r. All right. And then we also know that the gravitational acceleration is a g m e over r squared. This is nothing but the small g, but at the surface of Earth, not far away from Earth, then its value is different, okay? That's why this is the more general impression. If you substitute that value here and rearrange terms, you will find this. So use this value of A in here, okay, and try to rewrite. You will get this relation. T squared is equal to 4 pi squared R cube over GME, or in other words, T squared over R cube is equal to 4 pi squared over GME. And this is the special case of Kepler's third law. Okay? This is Kepler's third law. Okay? And why is it a special case? Because we are taking a circular orbit. Okay? What Kepler says is that if you have an object, so it means the ratio of the square of the time period with the cube of the radius of a circular orbit is constant for all planets. All right. And why is it a special case? Because the actual orbits are not circular, they are elliptical. Okay. And in this case, this A is just the semi-major axis, not the radius of a circle. That's the only difference. And then you would get the general Kepler's third law. Okay. That is Kepler's third law. And I'll just restate the second and the first law, and then that would be the end of the story. The first law says that planets move. So this is an ellipse. Okay. And you know that ellipse has 2 foci. Okay. And the sun is here. So the first law says exactly that the planets, all planets, move in elliptical orbits with sun at one of their foci. Okay. One of at the focus. Okay. And the second law says that a planet, the position vector of the planet, let me just make, this is sun. This is the position vector R. Okay. Let's say that after delta T, it is here. Okay. So the area that the position vector covers sweeps in a given time interval. Okay. Let's say that that is delta A. Is the same for equal intervals. Okay. Let's say that the planet is moving here. Okay. And now it would have to have a big angle, because otherwise to get the same area. So let's say that it moves delta A time, in delta A interval, it covers this much area. So delta A here and delta A here, if the time was same, delta T, then these delta A's would be the same. Okay. That is what Kepler's second law is, that the position vector of a planet in elliptical orbit, sweeps equal area in equal intervals of time. What that means is that when the planet is close to the sun, it goes very fast. When it is away, it goes slowly, because now the position vector is much larger. It just has to move smaller distance to get the same area. Okay, that is the second law, Kepler's second law. All right, and third we already discussed, and that's it.
Sir, first law आप please एक दफा repeat कर सकते हैं?
जी?
First law आप repeat कर सकते हैं?
The first law only says that the planets go into elliptical orbits with the sun at the focus of the ellipse.
सही। और सर दूसरा मैंने आपसे कहना था कि वो जो चैप्टर आई थिंक ये 8 है, इसके मतलब थोड़े से नोट्स तो अपलोडेड है, पार्ट 1 अपलोडेड है। कैन यू प्लीज अपलोड द रेस्ट ऑफ देम टुडे, क्योंकि मतलब क्विज के लिए हमने उनको पढ़ना भी है।
रोटेशनल डायनामिक्स वाले?
जी, वो उसका पार्ट 1 अपलोडेड है और कोई अपलोड नहीं हुआ हुआ।
ठीक है।